Hello everyone. Today we are going to talk about one of our accepted papers at EMBC 2025, as this one was presented in a format of a poster. So I thought about adding a video for those interested to explain what it's all about. So the title is Temporal Context Informed Myoelectric Feature Extraction and covers frequency invariance in EMG-based gesture recognition. The author names are shown over here, and this is presented today by myself, Rami Kushaba. So let's dive in. So a bit of background about this problem. So human-machine interfaces driven by EMG signals have long been utilized in this field for controlling prosthetic arms, and this is typically done using a cross-sectional pattern recognition scheme. So with cross-sectional models, we usually use a window, to review a short period of EMG signals and make decision based on that without relating it to the previous windows, basically. So the surge of utilization of deep learning models slowly shifted the focus from the traditional approaches into more powerful but complicated, memory demanding, and often clinically infeasible DL models. So the main difference here basically is that, as we say, the traditional approach was cross-sectional. You were looking at a small window of the EMG signal, extracting features, passing that to the classifier, making the decision. With these models, some of these models, of course, you tend to review the history or the temporal evolution of the EMG signal, not only the content of one window, but relating that to the previous context, and then extracting or generating your features and submitting that to the classification section. So models like CNN, TCN, LSTMs have been successfully employed in pattern recognition tasks to enable accurate real-time identification of hand gestures in the labs. So while these models have been heavily utilized in the literature and several papers are out there, we have to say that the suitability of deep learning models for clinical real-time based prosthesis control depends on several factors. So these could include, for example, computational cost, hardware limitation, and the need for model interpretability. So CNN, as you may know, they are very suitable for extracting the special features of the EMG, or let's say the features that describe the relationship between the muscles when a certain movement is done. So keep in mind that when you are actually implementing a certain hand movement, it's about the co-activation of the different muscles rather than the individual activation of individual muscles. So it's not about what one specific muscle is doing, it's about what these muscles as a group are doing. So these models, like CNN models, they are very good at extracting this aspect of the information, but they are computationally demanding, and they do not capture the temporal dependency. LSTM models, on the other hand, they excel at capturing or modeling the temporal dynamics, but they require more memory and processing power, which poses challenges in real-time embedded deployment. TCNs offer parallelism and competitive performance, but they also have a problem in terms of large memory footprint. They may require tuning basically. So while these models are powerful and they have been reported in several different publications, some of them even doing real-time tests, embedding such models in prosthetic control systems remain a challenge because of the computational cost and the memory requirements. While it's generally well known that embedded hardware may have limitations on in the wearable medical devices basically. So these models, in general, we tend to say they are difficult to implement on devices with limited resources, which emphasize the clinical application challenges. However, are we overstating this by saying these models are demanding? So while traditional LSTM, CNN, TCN are indeed very heavy for most computationally low power embedded prosthesis systems, researchers didn't stop at that, and they have been continually making progresses in terms of creating a lightweight version of these models, using, for example, quantization, model pruning, knowledge distillation, TinyML framework, and hardware-aware neural network architectures search. So that said, these models still not mainstream in commercial prostheses, mostly due to power and size constraints, regulatory burden of validating complex models, and preference for simple, explainable, and robust models like LDA, SVM, or decision tree. So what are we doing here today? We are proposing, let's say, a more justified or more of white box version of these models. We are focusing on the hybrid of the traditional approach, the feature engineering approach, and the deep learning models, basically. So what we do in the hybrid model, we learn how these models are working, what they are trying to do, and we try to replicate that in terms of feature engineering. And by that, we are actually creating more explainable kind of models. So not only saying there is a black box doing something, give me a result, I don't know how it's generated, good luck. No, it's not like that. You have to justify and you have to track the outcome, especially when you get audited or when you get a patent like approved or something like that. So our focus is on the transparent models, let's say, and the benefit of such models include the simplicity and the low computational characteristics of the traditional approach, the memory concepts and the spatial information extraction concept, which we can adopt from the deep learning. And we also add some positional encoding, like phases that we represented in the EMBC last year. So let's explain in further details. So the first component is focus on the spatial information extraction. What do we mean by spatial relationship or information extraction? Consider this example with a Myo armband where you have 8 EMG signals and you typically use an overlapping window scheme. In the typical approach, we extract information from the individual windows belonging to individual EMG time series or channels without relating the activity in one window to the activity in the nearby channel or sensor. What we are saying here today, we should be, if we want to extract the spatial information, we should be relating each of these sensors to the remaining sensors. So in this example, I'm showing you that we are going to relate the activity of channel 1 with channel 2, channel 1 with channel 3, and so on for the remaining channels. And this applies on all the channels. So let me explain further. Dismantle a Myo armband, you will have 8 EMG sensors, 8 physical EMG sensors. In one approach, we suggested to use range spatial filters. So what these filters do, you give it two input channels or the signal collected from two input channels, let's call them channel A and channel B, and they will give you a new signal, virtual signal, based on the maximum of the two minus the minimum of the two, and we call this channel C. So I will be relating the first physical to the second physical and generating the first physical to the third physical and generating the second virtual, and so on for the remaining physical and representing the remaining virtual channels. So up to this point, if you have CH number of channels, you will end up with CH times CH minus 1 divided by 2. And that will be the total number of total generated virtual channels. Why? Because you will repeat this process by fixing the reference first on channel 1 as we did, then 2 and the remaining, 3 and the remaining, and so on. So in an example with 8 physical, you will generate 8 times 7 divided by 2, which is 28 virtual channels. So instead of working with 8 physical, we generated 28 virtual channels. So in one example I show you over here, consider this example where channel A is the black, channel B is the red. Take the maximum of the two minus the minimum of the two, and this is what you get. This is the channel virtual that you have created. Why we do this? Because we wanted to capture the relationship. How do I capture the relationship? I did it in the simplest ever approach. Similarity, difference between the maximum and the minimum of the two, basically. You can do whatever approach you want to test. Go ahead, enjoy that. So this was published in EMBC 2019, and at the time we showed that by implementing this technique, with any time domain features, you already enhance the feature extraction, or this feature, let's say, classification accuracy. So if we move forward, if we think now that we have generated a set of virtual channels, Now what we need to do is extract features from each of the virtual channels, as if we have a set of physical channels. Okay, but the main difference here is that our virtual channels, they represent somehow the relationship between the channels. So we thought about feature extraction and we said, okay, let's start with something very simple, which is the waveform length feature. If you don't know what the waveform length is, imagine any signal, hold the two ends of it, stretch it out. That's the waveform length that this feature is calculating. So imagine another example where this time you have 10 electrodes, and this is the phasor representation across these electrode positions. So in one example, again, where you have an armband, for example, with 10 EMG channels, I am going to generate a new set of virtual channels using the same technique we just described. And instead of extracting waveform length from each of these individuals to have 10 WL values, we are going to have what? A set of virtual channels, and I'm going to apply the waveform length on the C, the combination or the virtuals that we have created, normalize that by the summation of the signals squared from the first channel and the second channel. Added to this, what we also did, we added a phasor component to represent the location of that channel on the forearm. So this is a cross section of your forearm. If you chop the hand from here and look in this direction, this is what you're going to see. In last year's EMBC, we extracted the features, encoded them with a phasor to represent their location, and then we said all what you have to do is any two channels, take the maximum minus the minimum, generate C, calculate the waveform length, normalize that, and add the position. And at the time, which was specifically last year, we showed an EMBC in our paper titled Modern Myoelectric Control, Is It Time to Change the Algorithmic Focus? We said, look, something simple like this, without any complication, is already showing value, and it's competing with state-of-the-art deep learning models like Rocket, Mini Rocket, or even LSTM and other models. So at the time, we were questioning, do we really need the very complicated deep learning models if something like this is generating like similar, let's say, classification results with much lighter computational cost? So this is what we have done previously, and now we are going to add another component or another layer on top of this, because now we captured the spatial information in a certain way, which is represented over here. We move to the second component now, and we focus on the temporal memory extraction. Referring back again to the Myo example, 8 EMG signals extracted from each of the sensors, overlapping window scheme. What we say over here, we typically extract information from each of the window without relating to the previous windows. So it's a cross-sectional typically. However, we want to change that by relating it to the activity in the previous window. Which previous window? Should I do the first previous, second previous, third previous? Which one of them? And how backwards should I, how much backward like should I go? Do I need short-term memory? Do I need long-term memory? Which one of them? To be honest, in the beginning, we didn't know. And we started exploring. And we found that actually using the two components, concatenating the two components, actually gives the best result. So what we did, we said, okay, let's generate or let's extract a short-term memory component where we relate the features of the current window subtracted from the features of a previous window, nth position, differentiate the two, multiply by the features of the current window, and by that you are emphasizing the changes across these feature dimensions and relating that to the current window. And this is the short-term memory component. What we have also added over here is a long-term memory component, and this is calculated by exponential smoothing with a parameter alpha that you can control yourself as a user. So a short-term memory component concatenated with a long-term memory component, and we say, let's go with this approach. And we decided to test the accuracy of this approach. However, it's important to mention that as we submitted this paper to EMBC 2025 in January 2025, there was actually a paper coming out from Google at the same time at around 31st of December 2024. It's called Titans Learning to Memorize at Test Time. So they were doing something similar in a slightly different approach, and they were saying an event that violates expectations is more memorable for humans. Inspired by this, a simple definition of surprise for model can be its gradient with respect to the input. So if I refer back to what we were doing over here, differentiating and relating it to current input, it's somehow in the same line of thinking. And we were happy that we are on the right track, because also Google was actually doing this and concatenating different forms of memory representations, including contextual, core, and persistent memory, as you can see over here. So we were happy that we believe and we are on the right track. So we adopted two databases for the testing. So the first one of them was the 3DC with two armbands on the forearm of the users, 22 intact limb subjects with 11 classes, two armbands collecting the signals at the same time. One of them is 3DC at 1000 Hz and the second was Myo at 200 Hz. On the other hand, we collected our own data from amputees, 6 amputees, performing 17 classes of movement, of course, imagining or performing that with the remaining muscles, residual muscles after amputation, as you can see over here. And this was done by using the Myo armband with 200 Hz. When we generated the classification results, we wanted to use, let's say, an industry, let's say a benchmark, well-known benchmark tool, and we selected libEMG, which is available for free online from New Brunswick University. So we use this toolbox. It has an amazing set of features implemented for you. All what you have to do is plug in your data and start testing. So we inserted our new method. We called it Wave LSTM, and we calculated the results for the blue armband, the Myo armband, and the orange, which is the 3DC. And then we ranked the results based on the average accuracy across the two armbands. So by that, we noticed that our method was actually the first from the left, which means the highest accuracy, average accuracy across the two armbands. Now, when we zoomed a bit to see what's going on over there, because the list of feature extraction methods was huge, 58 methods that we managed to overcome. So if you look at the results over here, most of these feature extraction methods, including LS4 and LS9 that were recommended by Finyamark's paper on wearable EMG armbands, so most of these methods, they achieve better classification results with the 3DC armband and lower classification results with the Myo armband. This is simply attributed to the fact that this one has a higher sampling frequency and this one has lower sampling frequency, and people usually say, okay, it's because of the sampling, more information, and then you get higher accuracy with one than the other. However, when we looked at our method, the difference wasn't really statistically significant across all the subjects, and we were saying, hang on, what's going on over there? How come this method is generating nearly the same results? So we looked closely at the results with and without normalization, and we noticed that it's like the results are not significantly different between the Myo and the 3DC armbands. Keep in mind, this one has 200 Hz sampling frequency and this one has 1000 Hz sampling frequency. And the same trend was generating with LSTM, applied on raw EMG data. This could be tweaked further, but we tried tweaking this on this data set, and this is the result we got at the time. So this is really something that needs further investigation. So we went ahead and started testing on the MPT data just to verify that Wave LSTM is actually doing better results or better performance. It's not really tied to one data set. So we tried it on the other database of 6 MPTs, and our method was actually achieving highest accuracy on average across the different classifiers. So in conclusion, our experiment revealed that, first of all, Wave LSTM, within the context of our experiments, it outperformed 58 established methods from the libEMG toolbox. However, this might be seen by some researchers as just merely another feature extraction method. But the real breakthrough, we believe, basically it lies in the invariance of the wave LSTM to the armbands with varying sampling frequencies. So as we said, we have tested on the 3DC and the Myo armband, but we are currently also testing on datasets collected by using the GeForce Plus. And keep in mind, this is one of the few in the industry, if there is any other armband, that allow you to change the sampling frequency and the ADC bit resolution. We can actually show the same trend, and we are preparing the journal publication, which shows that wave LSTM can actually achieve the same result regardless of the sampling frequency, even on the GeForce Plus, and this is an upcoming work. So today, what we want to reveal over here is that by making the algorithms transparent, we uncovered a potential for designing lower complexity hardware, because you can go with lower sampling frequency if your focus is only about gesture recognition. And this is especially advantageous for computationally efficient wearables, and this is a growing interest in consumer applications. So stay tuned for the upcoming journal papers. Thank you very much, and I hope that you have learned something new today. Thank you.